This is lecture 2, system thinking. This is part 2 for this lecture for the course IE4399E, Introduction to Systems Engineering, IE5397, System Thinking and Analysis. As always, I'd like to list the references that were used when preparing this lecture. So for this particular lecture, we're going to be using the material from chapter 1 on the Hitkins book, Advanced System Thinking, Engineering and Management. Today's lecture is going to be short. This is going to be complemented with the case study that you're going to be working on your own. And the agenda for today is to discuss the classification of systems. And then the second part of this lecture will be you to work with the case study assigned for the material covered today. Classifying systems. There are several ways to classify systems. For example, by complexity, morphology, or the principal content. There are basic shapes. Many systems can be identified by shapes. For example, airplanes, cars, when we look at processes or activities represented on a graph. So you can identify them by looking at the shape. Other systems can be identified by or classified based on their layer architectures. So many systems are layered and information has to pass through these layers. For example, security systems, chemical processing plants. If you're familiar with computer science, the internet firewalls, and many others. They're classified also by linked closed loops. Many systems comprise of loops, often operating antagonistically. For example, population, system of creating new members by this social cycle, birth system of discarding all members, the death. Also, many systems or many man-made systems are reminiscence of humans that designed and created them. For example, the jet fighters, the automobiles, and many others. If we classify system by the principal content, we can look at people systems. Many systems that interest us involve people, and they perform various functions, usually to support humans. For example, organizations such as universities, temples, churches, and so on. We also have social systems like schools and so on, and also the economy. We also have what are known as technological systems, which are the ones that typically involve systems engineering. And those are typically an outcome of their time and culture. So for example, the development of the cell phone and other devices such as the iWatch that is presented on this figure. Continuing with the principle of content, the composite information decision action, or IDA systems. These are some human-made systems are composite. They're part human and part technology. Some examples include the air traffic management, which controls the aircraft around airports and flight corridors. Also, the stock market. There are multiple medical systems that are part human and part technology, and also military weapon systems. Information decision action systems, or IDA systems, receive information presented to a human operator, and the operator makes a decision based on that. These type of systems, they tend to operate at high stress levels. When you think about the person in charge of air traffic management systems, they're dealing with a lot of information and they have to make the best decision with the information they have on hand. For example, deciding which airplane is going to land on a busy airport. Same thing with medical systems. A doctor that is trying to make a decision for treatment for a patient, looking at the profile of the patient, looking at the electronic records, looking at the surgeries, and let's say the genetics based on family history. Using all that information, you need to make the best decision in terms of what treatment to recommend to the patient. And if we think about military weapon systems, same thing. You have information about where the enemy is located, but at the same time, you have other people that can get affected if you deploy a specific weapon on a specific area. So decisions in terms or information about when would be the best time to pursue a specific attack, maybe information about forecasts in terms of when the enemy is going to be in certain locations, and so on. So again, the idea is that you have, for this principal content or this type of classification of system, you have part human and part technology, and they are working together. We can also classify system by behavior. In this classification, we have linear systems. These vary the response to stimulus by producing output that is proportional to the stimulus. So for example, mechanical level and the gear train for an engine. So for example, the distance the load move is proportional to the effort. And these type of systems, they have a highly predictable behavior. One example that is presented in the picture is a wind turbine. A wind turbine has a shaft. In order for this shaft to move or rotate to generate the power or the electricity, you have to have wind. So we call this a linear system because, you know, if you have information about the speed of the wind, you can predict how fast these blades are going to move and how fast this shaft is going to rotate. And using that information, you can have an estimation of how much power this turbine is going to generate. Obviously, there are other parameters that you have to take into account in addition to the wind speed. Things such as the size of the blade, the reliability of the components of the turbine, and so on. Another classification by behavior is called the quasi-linear. There are many systems that are quasi-linear. What this means is doubling the number of workers on a given task versus the task duration. These are examples that are typical in the manufacturing environment. So you had to accomplish, let's say, 1,000 units for your customer. So let's say you had to produce 1,000 units. So you had two ways to achieve that goal. You can increase the time. Let's say you have one shift of employees or staff working 8 hours, and that shift can only give you half or 500 units. So if you know that you can get 500 units with one shift, in order for you to get 1,000, you might need to extend that shift for another 8 hours. So, or that's in terms of the task duration. The other option you have is to run a second shift in which you are going to increase the number of workers. So that's the bullet. That's what the bullet is trying to express. So quasi-linear in the sense that you have two ways. Yeah, doubling the number of workers on a given task versus just increasing the task duration. Or depressing the accelerator on a vehicle versus the vehicle speed. Nonlinear dynamic. Many real world systems are nonlinear, such as biological systems, disease and natural disasters, ecologies and economies. So what this means is there's a high level of uncertainty in terms of how these systems can behave, and the outputs of these systems are not necessarily predictable, or they can be predicted only to a certain degree, because there are many factors that are affecting, and these factors are, all of them or most of them are uncertain. And then we have the chaotic, which chaos has a mathematical defined meaning to the scientists, but the term is literally used to indicate a situation out of control. It is remarkably difficult to classify a real-world system as chaotic in the mathematical sense. For example, earthquakes, stock market prices, distance between cars on a busy road, increases or decreases in annual crime figures. So that was the last slide for this lecture. Again, in this lecture, we focus on different ways of classifying systems. And now I'm going to let you work with the case study associated with this lecture. So please use the rest of the time to work on the case study. I think you'll find that case study very interesting, and I'll talk to you next time.